Yeah, so I'd like to start. Welcome, everyone. My name is Jan Barowski, and I have the pleasure here today to welcome Jasmin Grosinger from Technical University or University of Technology, Graz in Austria. And yeah, she will have a talk on radio frequency design for sustainability. But first of all, I'd like to introduce Jasmin a bit. So Jasmin Grosinger is an associate professor at the Graz University of Technology in Austria and a visiting associate professor at the Tohoku University in Sendai, Japan. Since 2013, she has researched ultra-low power microwave components and systems at Graz at the Institute of Microwave and Photonic Engineering. Jasmin is an IEEE senior member, and her research has resulted in more than 60 peer-reviewed publications and patents. Jasmin is actively involved in the technical program and steering committees of various microwave-related conferences, and she is an associate editor of the IEEE Microwave and Wireless Technology Letters. She is also a member of the IEEE Microwave Theory and Technique Society, MTTS, and was selected as a distinguished microwave lecturer. Since last year, she has also served as an elected voting member of the MTTS AdCom committee. So Jasmin, it's really a pleasure to have you here. I'm looking forward to your talk, and yeah, the stage is yours.
Thank you so much, Jan, and I'm very happy to be here with you. First, maybe a bit of a disclaimer. I do have a cold, a bit of it, so if I'm coughing once in a while or taking a sip of my water, please apologize. The title of my talk actually gives away its content as it should be. It's radio frequency design for sustainability, and I want to give you in the beginning a motivation what I mean by that. So if you think of the digitalization of economy and society that we will experience in the next recent years, we'll see that we have to expect a massive deployment of wireless devices, wireless sensor nodes, wireless communication nodes. And this comes together actually with the figure that you see here in the back, where we speak about the Internet of Things or the connectivity for everything, where each single device of our daily lives and also in our economy is connected wirelessly to the Internet. And one estimate of wireless nodes in our environment is 10 to the power of 7 devices per square kilometer. And that is a massive amount of devices. And if you think of deploying these amount of devices actually in our environment, and each single wireless device needs a battery, then you see that we create some sustainability issues with deploying these devices on environmental level, if we think of the batteries that we are using and their eco-toxicity, and also on economic level, if we think of the costs related to production of these devices and end-of-life costs related to these devices. So what I do in my research is to translate these sustainability issues that arise with this massive deployment of wireless devices into radio frequency design challenges and solve these challenges to have, at least on our end as radio frequency engineer, to reach on our end sustainability for these devices. Let me give you here some examples. I've already mentioned batteries. So if you have, oh, please apologize, if you have batteries with all these devices, you will see that the ecotoxicity and the end of life of these devices, all these batteries, that is very troublesome in terms of environmental sustainability. And also, if you think of, we need to replace these batteries once in a while. Oh, I'm very sorry for this. Or we have to replace these batteries once in a while. This is a very cost-intense task to do. So what we do in our group is to use exclusively ultra-low power wireless communication technologies to get rid of batteries, or if we are not able to get rid of batteries completely, to at least have an ultra low power consumption and to extend the lifetime of the batteries to 10 years, for example. So, and on the other hand, what we can do as radio frequency engineers to increase the sustainability of these wireless devices is to reduce their carbon footprint related to their production, but also to reduce the footprint of the devices in general, to use less rare material that we would need for the production. And in particular, if we think of production and end-of-life costs, we also have to find a solution, a way to decrease these costs. And one solution is to use a high level of integration and to miniaturize these devices and to use less and less, or to reduce the carbon footprint also, and reduce the carbon footprint, and also to use less rare material for them. In this talk now, I want to give you an overview of recent solutions that we presented in the last years. As you can see here, a full-fledged wireless sensor device that operates without a battery. The power that the device needs to operate is provided wirelessly by an interrogator or reader. And in this talk, I want to focus on one specific ultra-low power wireless communication technology that is very much a technology that you'll find around here in the Graz region and in the south of Austria. It's the RFID technologies, radio frequency identification. And there we have two frequencies we can operate and follow the standards that are available. We have high frequency RFID technologies or UHF RFID technologies. And as I said, here in the Graz region, we do have an RFID hotspot, so to say. We have a lot of companies from the semiconductor industry to system level providers that share actually that work on RFID. We have NXP Semiconductor, we have Infineon, we have other system level providers, or companies focus on the reader, companies focusing on the middleware, all these things. So RFID here in Graz is quite big, and the good thing about RFID is that you can operate batteryless because you provide the power towards this little transponder device or short tech. And for reaching the high level of integration that I mentioned, which is also important for a sustainable device, is we use CMOS technologies, complementary metal-oxide-semiconductor technologies, and coming with them means to reduce the size of the devices by exploiting system-on-package, SiP concepts, or system-on-chip concepts. And here, this device that I show you here is following a system-in-package approach, and we use here wafer-level packaging technology provided by Infineon. And in this talk, I want to give you more information about how to miniaturize RFID transponders, tags that we use for communication or for sensing. This here is a sensing device, and I will give you more details on it. But first, let me introduce to you the RFID technology. We have these two standardized technologies available. At the lower frequency end, at high frequencies, we operate at 13.56 megahertz, and we have a reader, as you can see here in the back, and a transponder, communication or sensor device, as you can see it here in the front. And both devices operate with each other's near field. They are both magnetically resonant at 13.56 megahertz, and if they are in the near field of each other, we are able to provide power from the interrogator device to the batteryless transponder. And then if enough power is available and the interrogator commands, the transponder can send back its identification number or sensor information. The communication distance that we can reach in this near field communication technology is up to 10 centimeters. And actually, you use it very often nowadays for contactless payment, where we use the NFC standard that is denoted in the ISO IEC 18092 document. And here we follow the so-called proximity standard of HF RFID. And near field communication, NFC, that we use for payment, is a derivative of it, and was actually invented here in the Graz region by NXP Semiconductor by Franz Amtmann. Another possibility to have a bit of more extended read range, but still rely on near field communication, is following the vicinity standard, where we have a read range, a communication range of up to 1 meter. The second technology, RFID technology, that we have available relies again on the communication between a reader, the interrogator, that provides power and data, towards a tag. This time, however, we operate at higher frequencies, and we have here licensed frequency ranges from 860 to 960 megahertz. And here we follow usually the national guidelines. So in Austria, for example, we operate at 868 megahertz. In Japan, you would operate at 950 megahertz. And the means how to communication and wireless power transfer is established is actually in the far field. And we rely on electromagnetic wave propagation, transmission and reception as both devices, at the reader and the transponder. And here in the back, you can see a transponder device, a normal sized one with the chip, and connected to it a meandered dipole antenna. To the meanders you're using usually to decrease the size of the antenna a bit, but in the end, it is a dipole antenna, and it needs to have roughly half the wavelength in size. The read range that we can reach here is 10 meter, up to 10 meter, and it really depends on the wireless propagation environment you're in and on the wireless channel. And this is very often the bottleneck of UHF RFID, because at the tag, the sensor device, at the communication device, you operate battery-less. So the wireless power transfer has to be in the far field very, very nice and accurate. And also the channel has to allow for it, which is not always the case, in particular if you are in a multipath environment. So lots of challenges here that we have to actually solve. Now, if we take a look at the usual tag sizes at HF RFID at 13.56 megahertz, the usual tag size is a credit card size of 8 to 4 centimeter. And this is the class 1 antenna following the standard. And we very often have also this type of antenna for contactless payment, in particular with our credit cards. And for UHF RFID, as I said, we would need half the wavelength, and at 1 gigahertz, this would be 15 centimeter for an efficient antenna. Usually it's a bit smaller because we prefer power matching before having a resonant or a half-wave dipole resonance. But still, you know, you can get in the range of 10 centimeter, maybe a bit smaller. But usually, as soon as you make the antenna smaller, it's less efficient. And if we think of now reducing the footprint of the devices to use less rare material and have a lower production cost, then if we want to miniaturize these tags, these transponders, then we have to miniaturize the antenna. And as soon as we miniaturize the antenna, and we still operate at our frequencies, which are standardized, 13.56 megahertz and 860 megahertz, then we have to deal with the read range reduction. And this is what you can definitely do. So we focus for miniaturization then on near field communication for HF RFID as well as for UHF RFID. And then we rely on coils to establish magnetic resonant coupling or inductive coupling, or electrodes where we use capacitive coupling. If you now take a look at the different miniaturization classes that are out there and their area sizes, you can see here conventional size tags. here the HF RFID tag in its credit size card form, or a UHF RFID tag. And usually you can miniaturize the tags down to 200 square millimeter, but you will not find conventional size tags that are smaller and give you the same performance. What you then can do to really miniaturize also the antenna and the coils, you can put the coils on the package. And these are then system in package based tags, and you can see here 2 classes of them. And then you can reach sizes of bigger than 2 square millimeter, which is already quite small. And here I have a coil on system tag that I want to show you in more detail, because it comes with everything that we need for communication and for sensing is included in a single package, as I mentioned it before. And then we have a coil on module tag that is used nowadays with Infineon products. It's an Infineon product for credit cards for payment. And then you can see here, this is the top side that you see when you take a look at the credit card. Here you have the contacts for contact-based payment when you insert your card into the payment terminal. And then on the other side, what you'll find with this coil on module Infineon product is you have here the chip on the package, and then connected to the chip, a coil, and the chip and the coil then resonate at 13.56 megahertz and allows you then to establish HF RFID communication for payment, or near-field communication for payment. And what's quite interesting is, and I will show you a few slides on that, is if you have this usually in your credit card, this coil on module, then what you will find also in the credit card immersed is a passive booster antenna. And I will show you the detail of this, but the functionality of this passive booster antenna is to extend the read range of this miniaturized coil. Because with system in package-based tags, and if we go to these area sizes, as I mentioned before, we usually have then a read range of a maximum of 1 centimeter, and that's it. What you then can do to even more miniaturize the footprint of your devices is to use system on chip based tags. And then you can get down to an area size of 1 square millimeter, or even smaller. And you can see here 4 prototypes that we realized together with Infineon Technologies here in Graz. Here you see coils on silicon, 2 types of coils to operate at both frequencies at 13.56 and 860 megahertz. And here we use a dual band front end, or some other tags at HF and UHF. And here a so-called OC3 tag, on-chip capacitive coupled tag, that uses capacitor, actually electrodes and capacitive coupling for communication. And I will give you more details on this one too. But in the end, what you will see is here for system on chip-based tags, you will not find any products yet, just because the read range is even more shorter. It's down to a few millimeter. And then you're lucky already, in particular for capacitive coupling. But, you know, some applications are good with this few millimeter read range, and it's a battery-less device. So we should definitely use it if the application is up for it. Oh, sorry. So this adventure on miniaturizing tags actually started back at the French Telecom at 13.56 megahertz. And they published there a system on chip tag, a coil on chip tag in 2000, operating at this frequency. However, they never successfully showed read range measurements. So it really took a while until in California at Broadcom Corporation, Shameli et al. Presented then in 2007 the first coil on chip tag that also showed successful read range measurements at 900 megahertz. And it took then another few years to establish successful communication at the lower frequency with the higher wavelength at 13.56 megahertz. And this was in Japan at the Nagoya University. And you can definitely see it's always a battle achieving first on the communication at 900 megahertz for a coil-on module by Hitachi Chemicals in Japan, and then at 13.56 megahertz, which is even harder to establish because the performance is even worse at 2012 by Murata Manufacturing, also in Japan. And it was actually us, Infineon and Graz University of Technology, that showed the first OC3 tech, where we use capacitive coupling and dual band operation and the successful read range measurement, and also this coil-on system tech, where we have a full-fledged sensor functionality on top of the communication functionality. And I want to show you more details on these two prototypes and what you have to take care on for miniaturizing, so that you can take home these learnings from this talk. Another thing is, as I said, the application is very important. And if you think of point of care testing for our coil-on system tech that I showed you before, we can put the coil-on system tech here. Then we have here a test stripe, and then fluid with magnetically marked biomolecules that we can then detect with our impedance sensor. And in this case, for this tech prototype, really realized a maximum read range of 11 millimeter, so roughly 1 centimeter. And here you can see the reader device. And for such point of care testing, as you can see, that's quite feasible to have a 1 centimeter read range, because for the application, we can serve it. However, if you want to have an extended read range, because it's not point of care testing, but something else like payment and coil-on modules as provided by Infineon, then you can use these so-called booster antennas, as I mentioned them before. And the booster antenna looks like this roughly. You have the little tech product or the coil-on module with the coil-on package. And then you have at the booster antenna a small coupling structure that has the same size in terms of coil as you have it on the tag, on the coil-on module. And then you align these two things, also in the credit card and embed it, and then you're able to establish a longer read range just because this small coupling structure is connected to a bigger coupling or pickup antenna, so to say, so that you're able to harvest more power provided by the interrogator, and you can then extend the read range. And this is done with these coil-on module products in combination with the booster antennas for these credit cards. And the advantage of such a realization is, of course, you can extend the read range, that's one thing, but also you don't need any galvanic contacts between the coil-on module then, that is a full-fledged tag, and the booster antenna in the credit card. Because it is actually quite vulnerable to have a galvanic contact, because if the user bends the credit card, it can break, and it is then less mechanically stable and robust, which is not so cool for the user. And the other thing is you have an easy assembly process, just because you don't have to need any galvanic connection between the coil-on module and the booster antenna, and you then have a reduced fabrication cost, which is always a factor, as we know it from our previous discussion of economic sustainability. And another benefit is you can use individual booster antennas for one tag product. So if you have a dual band tag, you just have to change the booster antenna and you're able to communicate at HF or at UHF. That you get a better feeling of how this works, the coil-on module with the booster antenna. I show you here a movie. And you can see it's a movie provided by Infineon with the coil-on module. Here is the coil-on module with, of course, a very secure chip. And at these short read ranges, we are able to provide the power to have a lot of security on top. Here you see the payment terminal, and then the coil-on module and the booster antenna embedded in the credit card. And by this, you're able to achieve a communication, a payment experience for the user that has, the read range that you are looking for or that they are used to. And it's a very interesting thing. One thing maybe you might bring up is then, so if the booster antenna extends actually the device size again. So the booster antenna ideally should be, if it's, if we target a sustainable, environmentally friendly device, the booster antenna actually should be then made of biodegradable material. For the substrate material, we are there yet. However, for the conductive material, there we are still lacking material that has a very high conductivity to also allow communication with a battery-less device. But that's something we also have to solve this challenge to realize full sustainable devices there. Now, let me give you some insights of this coil-on system tech with the point-of-care testing that I mentioned before to detect magnetically marked biomolecules. It was a European research project together with many other partners and together with Infineon in Regensburg that provided the packaging technology that we used to immerse all the components necessary in one single package and to realize this full-fledged sensor node operating battery-less. You can see here a computer tomography of the device. We have here an impedance sensor, some vertical interconnects realized by the read distribution layer in the packaging technology. And here we have then the red thing is a biochip to detect tunnel magnetic resistance and to detect then this biomagnetically marked molecules. And also then in blue, we have the communication chip, and connected to the communication chip, a coil that is embedded in the fan-out area of the package. And the cool thing about this packaging technology is that it's on wafer level, which gives you some decent cost for these devices and brings down the cost. So our part here in this project was to establish communication, wireless power transfer and communication to power up the device and read out the sensor data. And if you now want to design such an antenna in this fan-out area of the packaging technology, then you have to also take a look first at the whole system, at the reader and the tag. And to have a fast evaluation of your full system, usually we go into equivalent circuits, which are quite accurate at 13.56 megahertz. And here you can see then the reader chip, a matching network that we need, and then the reader coil. And for the reader coil, what we have is a very simplified equivalent circuit model for a coil, an inductance L that models the inductance of the coil, a resistance that models the losses in the coil metal, and of course other losses in the dielectric material. And then we have here in parallel the capacitance that models capacitive coupling between the various coil windings, also extended, of course, by the packaging material and its relative permittivity that we use there. So these three components to model the reader coil and the normal size coil is a safe thing to do, and it's quite accurate. On the other side, then we have the tag coil that I also show you here in this simplified model. And then between the coils, inductances, we have then a capacitive coupling coefficient that denotes then, okay, what is the distance between the coils and what is the arrangement of the coils in terms of angle or a lateral shift, any of these things. And it gives you then, as a designer, the possibility to vary for various coupling coefficients that you'll find in your application, to take a look at the full system and see if you're good to go or not. If you have enough power transfer towards the tag, and if you're still able at the reader input to detect the voltage change, which is created by this resistance change at the chip, to then demodulate, to detect the data provided by the tag and to demodulate then this signal that we received there. And here we have the tag coil attached to it, the tag chip that is usually modeled. You will also find this in the data sheets by a parallel circuit of resistance and capacitance. The resistance, as I said, is usually varying. And in particular, if you modulate, if you want to send your data, you vary from a high resistance level to a small one. And this, we use very often a shunt transistor to realize this. And this shunt transistor is also then used to protect the chip circuitry from over voltages that we cannot handle, for example. For 40 nanometer CMOS, we would not be able to handle more than 1.1 volt. For 130 nanometer, it would be about 3.8 volt. That we're okay still to handle, but the rest, we try to get rid of it by detuning the chip. But if you're interested in more details on what's actually the input impedance of these chips, of various chips, we measured them, and we also provide the data port material. So the data coming with these measurements of 16 chips, where we also have some NXP chips included. And then you can have, for your design, you can see the proper resistance and capacitance, take it, and then you can calculate the inductance that you need for your coil to establish this performance that you're aiming for your application, varying with coupling factor. And you can calculate this inductance by taking a look at this equation where we have the resonant frequency of the tag, which is 13.56 megahertz, and then where we have included the coil, the transponder coil inductance and the chip capacitance. And the rest we omit for now. But if you have the chip capacitance, and then you have the frequency, the resonance frequency, you can calculate the inductance. And this we did. And it was an inductance level of value of 2.33 microhenry that we aimed for. And we had the chip capacitance already for smaller sized coils of 56 picofarad. And resonance 13.56 megahertz, as I said, chip resistance from 8 kilo ohm to 40 kilo ohm. And what you then do, if as soon as you have the inductance value of your coil is, you go to a full wave simulator and model your environment, all the chips, the impedance sensor, the metal you have there, the package fan out area with a relative permittivity of 4.1. And then you design for this coil and hitting this inductance level. And in our case, you can see here the realization, it's 19 windings with a 20 micrometer track and gap width. And then with as we had the design available, we realized, of course, the prototype and measure it. And here you can see the prototype. The size of it was 6 millimeter times 4 millimeter and a height of about 1 millimeter. And the read range measurement, the communication range measurement we did here, we come in with a coaxial cable from the reader, a matching network, custom built reader coil to do appropriate measurements. We had 1 watt read output power, and we were then able to achieve this maximum read range of 11 millimeter that I mentioned before. And for our point of care testing, we were super happy about it. And we also showed then the application with our partners together. But if you want to exploit such miniaturized sensor nodes even further, also for applications where you're aiming for a higher communication distance, what you can do is you can use booster antennas. And here is a video where I show you a little coil-on system tag, a coil-on chip tag with a tissue bag on top filled with water just for demonstration purposes. And then you have here the custom-built booster antenna with this little pickup structure, coupling structure. And here is then the huge pickup coil to extend the read range. And what you can see is we have done a little app where we read out the communication, the communication chip. In this case, we had a temperature sensor on chip, which showed you then the temperature of 19.2 degrees Celsius. So various options here, and now I want to show you as the last part of my talk and the on-chip capacitive coupled tag, because it also gives you another perspective of how you can use an actually capacitive coupling to also establish communication with a battery-less device. We realized this OC3 tag, on-chip capacitive coupling tag. As you can see it here are various samples, and you can see it compared with its size to a 1 cent euro coin. And the area of the tag was 1 square millimeter. And we had then a top electrode and a bottom electrode. And the top electrode for capacitive coupling with the reader. The top electrode was actually a top metal surface layer, as you can see it here. And then the chip substrate acted as the bottom electrode of the tag and was connected to the chip ground. And we used the 130 nanometer CMOS technology. It was a collaboration with Infineon here in Graz again. And we had a dual band radio frequency front end at hand, operating at 13.56 megahertz and 868 megahertz. And advantages that come actually with capacitive coupling is you have a frequency independent operation. You don't need to hit resonance at 13.56 megahertz with a coil and the chip together. It's just a metal layer, top and bottom. With this, you also have reduced costs, because compared to having a coil on chip or just the top metal layer, the top layer fully metallized, that's a reduced cost that you have, and also increased mechanical robustness, because you cannot destroy any windings of the coil. And the other cool thing about on-chip capacitive coupling is that you can tag metal objects, which is very often a bottleneck with HF RFID and with most of the wireless devices that we have there. We have to think of means to make them operate robustly in metal environments, and using capacitive coupling is one means to do it. Of course, as I mentioned before, a disadvantage here with capacitive coupling is the very reduced read range. For the system design, you now have not coils anymore, but you have electrodes and a reader electrode and a tag electrode, a bottom and top, and they establish together then capacitances. So we have here again the reader on the left side of the system, an equivalent circuit model. We have here the tag chip, and then connected to the tag chip, the top electrode and the bottom electrode. And here at the reader, we have a top reader electrode and a bottom reader electrode. And these capacitances, you can then, that are realized by reader and tag electrodes, you can actually calculate using, the surface area, the distance between the capacitances, for us then the read range, and the information about relative permittivity. And what you can also see is you have actually a capacitive voltage divider at hand, where you have to make sure that the tag chip receives enough power to start up. And to establish this, you also have then to model these parasitic capacitances that you create by having a lot of metal layers in the silicon substrate with this high relative permittivity. And this you have to model too, to make sure, okay, I'm able to provide the voltage that I need here to establish then communication. We realized then this tag, and here you can see then the read range measurement to verify our prototype. We have the reader and the tuning structure with a reader top electrode and the reader bottom electrode. In the pack, you can see very lightly also the photograph of it, but I think the schematic gives you more details here. And the reader electrode on the bottom was actually a coin, so some metal. And we had again 1 watt reader output power. Here we have the OC3 tag included. And to have a distance between the bottom electrodes of tag and reader, we use a sheet of paper, which has a certain size height D2. And then the read range we define to be D1. So at the top electrodes, the distance of the top electrodes of reader and tag. And the read range that we were able to establish now with the sheet of paper in between was at HF 100 micrometer and at UHF 300 micrometer. And as you can see, that's a very limited read range. It's not even millimeter levels, but some applications are for sure okay with this. Think of Nespresso capsules, tagging them, and use then the Nespresso machine as a reader. So you have actually then a contactless setup, and you can read out then the tag data of your Nespresso capsule. If you want to have an extended read range, we have dual band functionality, so we can design then booster antennas to extend the read range again. And here you can then see the video of booster antenna for this OC3 tag for HF RFID applications. And what you have to think of, because you need the top electrode and the bottom electrode, this time we need two booster structures, of course, with the top electrode coupling structure and the bottom electrode coupling structure. And Walter demonstrates here how he aligns everything. And of course, we used some tape to really show contactless communication. And then you can read out the electronic product code of your device. And this is at 13.56 megahertz, but you can do the same thing, just an other booster antenna type for UHF, because it's a dual band tag. We have the UHF functionality. So we have then the same coupling structure for the booster antennas, but it's not the pickup antenna, it's based on a dipole, T-match dipole, and not on a coil anymore to establish communication using electromagnetic wave propagation. And you can see here then the alignment, and here the reader, and how we read out then the electronic product code. And that's one means, how you realize these booster antennas. And as I said, for really sustainable realization, we have also to work on the booster antennas and be able to have high conductive material that is biodegradable. That would be the best thing. Other things where we use the booster antennas is when we are in metal environment. And for example, with AVL, this is a company in automotive supply industry, and they have this Hydron device here, as you can see it, and they wanted to have a sensor inside, a temperature sensor, over temperature sensor, and to read it then out from the outside. There is a metal housing, and we use then the booster antenna technology and ferrite material in combination to have then to just need a little opening in the metal housing and read then out the sensor data. And then you can see the tag tamper status is closed. We use here an NXP sensor tag product. And it's quite neat. Of course, for a full sustainable realization, you have to get rid of ferrite material because ferrite is very rare and it's not sustainable. But what you can do instead of using ferrite to decouple from the metal environment, the coils, you can use metal materials. That's another option. And with this, I really want to thank you for your attention and want to just conclude that it's really on us as RF engineers to also contribute to more sustainability with all these wireless devices that come up. And in particular, I know it's very hard to establish a reliable communication with battery-less devices, but for us as researchers, there are still many challenges that we can tackle and work on. And I definitely believe that battery-less is one way to go, and we must go in this direction. Thank you so much.
Yeah, Jasmin, thank you very much for this very interesting and inspiring talk. To all people in the audience, I invite you to make use of our Q&A opportunities, either using the chat or the Q&A panel. And so the idea would be you just write down your questions and I would read them Jasmin, and yeah, let's hope that we have a bit of discussion. So while you're all writing, I may start with a question, maybe, Jasmin. I'm not sure if it's yeah, under the aspect of sustainability, but I have heard about millimeter wave RFID application and research a lot in the past. Can you comment on that? Is this part of your work as well?
Thank you so much for the question. It's millimeter wave is very interesting, in particular also with respect to miniaturization, and still have, you know, a good performance. And you see more and more publications coming up from this side. Definitely. The only thing which is right now lacking to use it for consumer products is that there are no standards yet available. So this would be something that has to be worked on and driven by companies to create standards using this. We also had once a collaboration with Infineon and NXP on using MMIDs, as they are very often called, so millimeter wave RFID tags. And there it was just an exploration. It was a few years ago, and still, you know, the measurement devices were very costly. So the companies were, you know, quite, you know, let's say they were then not that convinced, you know, that it's a way forward. But, you know, that was years ago, and the things change, and you will see also some very cost-efficient realizations of these tags at millimeter wave. So I believe that's a very interesting way forward. I'm not an expert in it, but I know there are some, and it's definitely one means to realize also sustainable solutions that maybe have a higher read range than the things that we have here, because it's still batteryless.
Okay, thank you very much. So in the meantime, there was a question. So the question is, as we are growing and moving forward towards the 6G technology, how can we ensure the sustainability in the environment with so much higher frequency? So maybe a bit of the same direction.
Thank you for this question. It's definitely very interesting, because when I'm in this research field where we operate batteryless, and then of course sustainability comes to your mind very fast, and all these challenges that come with it. But it's a very good motivation, you know, to go forward with your research. For higher frequencies, the motivation is still to, you know, to achieve or to realize the technology and to achieve what's possible. So sustainability is not that often in the back of the mind of the researchers doing 6G. From my point of view, but it still could, you know, it's still important also for the researchers working at higher frequencies to also think about sustainable realization. So for example, being able to have an MMID that is batteryless. That is one step forward, or reducing the footprint of the devices. There are means, and I know, for example, with the what's quite interesting also with passive radar, that might also become, you know, a very important thing within 6G. That passive radar is a sustainable way forward for radar systems in general. And I saw some publications there, and I think it's very interesting, because you just, you know, piggyback kind of another radar source or other transmitter source, whatever. It's very interesting, and I find it a good way forward with respect to sustainability too.
Okay, yeah, thank you, Jasmin. So there's another question. I just read. I'm not sure myself, but we'll see. So in the future, do you see applications of these booster antennas in quantum computers? I personally do not see the link yet, to be honest. But...
Yeah, no, wait. I saw an interesting talk at IMS in 2022. It was the keynote talk given by, I forgot the name, but it was the husband of Zoya Popovich in Boulder, Colorado. And he gave a quite interesting talk on how you actually can realize using quantum engineering to realize antennas that are independent in their operation of their size. And I have to say, I think that is very interesting because, you know, the size is very often very difficult for us. Of course, it's far away still in terms of, you know, really showing this and also showing this maybe at frequencies which are now used also at, you know, right now consumer products, they're just, you know, sub 1 gigahertz. So it's not relevant now. But, you know, if we go up also with consumer products to higher frequencies, it might get relevant sometime. And to be honest, booster antennas, they are frequency independent. You just have to design for them. In terms of, you know, you can use an MMID and the booster antenna and you're good to go. You could also use any other miniaturized wireless device or sensor device and create a booster antenna for it. But for quantum computers, I'm not sure there because I'm really not in quantum computers.
Okay. Yeah, so there is another question. In comparison to RFIDs in future, can we develop wireless charging? And by wireless charging, I mean plug in your adapter and your phone gets charged. So it's like a, what is meant? Is it an adapter that allows for the wireless charging? Jasmin, do you see the question yourself?
Yes, I see it. It's let me repeat it again. In comparison to RFIDs, in future, can we develop wireless charging? By wireless charging, I mean plug in your adapter and your phone gets charged. Actually, RFID has a lot to do and establish its you know, its battery-less operation by operating by wireless charging, so to say. We have to provide power wirelessly. And there is a new standard now out. Because if you think of consumer products, what you see is you can see the key standard that operates between 100 and 200 kilohertz, uses magnetic resonant coupling, and you have it already available for your phone. You just plug in then, you know, the transmitter device, the wireless power transfer transmitter device, the charger device, and you put your phone on top of it. And you have on top of, for the payment coil, an additional key coil. But what's now there is, as an add-on to the key standard provided by the Air Fuel Alliance, there is now a NFC charging, near-field communication charging that is based on HF RFID. And here, this is quite interesting. I speak with companies that are actually based here in the Graz region. We have still some troubles, you know, because NFC usually was realized for power transfer and communication, and now it's just used for power transfer again. So we have to revisit our designs a bit to have this in mind, and then do, for example, on-the-go charging of your wearable, because you're like somewhere hiking in the Alps and you still need a battery to and your wearable runs out of a battery and you want to have your vital data, you know how it is, and you just use your wireless phone, your phone with the NFC interface, and then quickly charge your wearable with the phone. And that's something that is currently in the mind of the companies, and it's something where we use RFID near-field communication for charging.
Maybe a question from my side that goes into a similar direction. So on my mobile phone or my wearable device, I can just download in principle my bank card, for example, so that I can pay with my phone. But then I have a very powerful system in the back. So energy efficiency and let's say maybe also matching and the transmit power in the end is more or less without limits. Are these front ends in their architecture the same compared to the completely passive devices? Because the active phone is mimicking a passive device, right? And it has less constraints.
Exactly. So this is, thank you for the question. It's near-field communication actually is an enhancement of HF RFID, where we also have the possibility that a phone can act as a reader or a tag. And then, of course, we are battery powered. So it's, and what I'm aware of, but I'm not a very, I don't have the full insights here, but what I'm aware of is that the designs are complete, that they are very different, so to say, because you just have more power available at the mobile phone. And it's a very, you don't have these challenges as with a tag that is fully batteryless. Yes.
Yeah, okay. And maybe another question regarding the sustainability and maybe tags that have a more or less limited life cycle. There are inks that are conductive. So I could imagine to just print the booster antenna, for example, on a piece of paper or something like that. Can you comment on the quality of these inks and the conductivity, as you said, is crucial. Is this sufficient for your applications?
So for the, we did some collaboration. Thank you for the question. So we did some collaborations with silver inkjet printing, and there, if have enough layers and enough curing and high enough temperature, you're good to go. So it's really not a problem. We even printed with silver ink on ferrite material to get independent of metal material for such HF RFID tags or NFC tags. But as soon as, I think with copper, you are still good to go, and it's a bit cheaper than silver, of course. But as soon as it comes to this biodegradable stuff, I think we are not there yet to really have enough conductivity, because we shouldn't lose too much power in our antenna structure or coil structure, because everything that we lose, that we don't have available for operation, and then it reduces the read range even more.
Okay. Yeah. Thank you, Jasmin, very much also for the very interesting discussion. I guess there are no questions anymore, so I thank the audience for being with us here. Thanks again to Jasmin. It was truly a pleasure. And yeah, bye-bye.
Thank you so much, Jan. Thank you so much for the invitation, and thank you for listening all. Thank you.
Yeah. Bye-bye.
Bye-bye.